For almost all of recorded human history, the velocity of human thought was held hostage by the physical speed of matter. If you wished to communicate with another human being beyond the reach of your own vocal cords, that message had to be physically transported across the surface of the earth. It moved at the pace of a running messenger's legs, the gallop of a post horse, or the speed of a wooden sailing ship navigating ocean currents and prevailing winds. If an empire stretched across thousands of kilometers, an emperor in a capital city had no ability to know that a rebellion had erupted on the frontier until weeks or months after the garrison had fallen. Peace treaties were signed in European capitals, while armies on distant continents continued killing one another in bloody battles, because news of the armistice took 6 weeks to cross the ocean. For thousands of years, humanity lived under the absolute tyranny of physical distance, dreaming of a day when human thoughts could travel instantaneously without moving a single gram of physical matter. To overcome this barrier, ancient civilizations engineered the first optical and acoustic signaling systems. Long before the discovery of electricity, human societies understood that light and sound travel far faster than horses. In ancient Mesopotamia, China, Greece, and across regions stretching from Egypt to Palestine, modern-day Israel, sentinels constructed chains of beacon fires on mountaintops by lighting a fire at night or releasing thick columns of smoke during the day. A garrison could transmit a binary warning of an approaching army across hundreds of kilometers in just a few hours. Yet beacon fires were severely limited. They were binary switches, capable of conveying only one predetermined message, such as danger or victory, with zero capacity to transmit nuanced information, tactical details, or unexpected developments. In the 4th century BC, the Greek military writer Aeneas Tacticus invented the hydraulic telegraph. One of the earliest attempts to encode complex messages across distances, the system utilized two identical cylindrical containers filled with water, positioned on distant hills within sight of one another. Each container was fitted with an identical drain faucet at the bottom and a vertical floating wooden rod marked with specific military phrases, such as cavalry arriving or infantry retreating. When the transmitting operator raised a burning torch, both operators opened their faucets simultaneously, allowing water to drain at an identical rate. When the transmitter lowered the torch, both closed their faucets and read whichever message was aligned with the vessel's rim. In the 2nd century BC, the Greek historian Polybius devised the Polybius square, converting letters of the alphabet into a 5x5 coordinate grid, signaled by holding up torches in the left and right hands, creating one of the first coordinate character encodings in history. Yet all ancient optical systems suffered from crippling physical limitations. They could transmit only a handful of prearranged phrases, and they were completely blinded by nighttime darkness, thick fog, heavy rainstorms, and adverse terrain. The first major leap toward a scalable national telecommunications network occurred in 1792 AD, during the turbulent years of the French Revolution. A French engineer named Claude Chappe, along with his 4 brothers, invented the optical semaphore telegraph. Chappe constructed a network of tall stone towers situated on hilltops within direct line of sight of one another, spaced roughly 8 to 15 kilometers apart. Atop each tower stood a massive mechanical apparatus consisting of a central rotating wooden beam, called a regulator, and 2 movable indicator arms called counterpoises. By manipulating iron control levers and counterweights from an operating room inside the tower, a skilled operator could position the arms into 196 distinct geometric configurations. Each geometric shape on Chappe's semaphore corresponded to a specific code number in a 92-page codebook containing 8,464 predefined words, military phrases, and administrative sentences. Operators in adjacent towers peered through brass telescopes, observed the configuration on the neighboring tower, duplicated the geometric shape on their own apparatus, and passed the message down the line. By the early 19th century AD, France had constructed a network of 556 semaphore towers spanning more than 4,800 kilometers, connecting Paris to naval ports like Brest and Toulon. A 3-symbol dispatch could travel from Paris to Lille across 230 kilometers in less than 2 minutes. Yet despite its brilliance, the semaphore telegraph remained an expensive, fragile system. It required an army of thousands of operators, cost 1,000,000 south of francs to maintain, and was rendered completely useless whenever fog descended. darkness fell, or snowstorms struck. Humanity still needed a signaling medium that was immune to weather and could operate at the speed of light through total darkness. The secret to instantaneous communication lay hidden within the mysterious forces of electricity. Throughout the 18th century, 18 natural philosophers in Europe began experimenting with electrostatic charges generated by glass friction machines. In 1729 AD, English scientist Stephen Gray discovered electrical conductivity, proving that an electrostatic charge could travel hundreds of meters through damp hemp thread, while being insulated by silk cords. In 1745 AD, Dutch scientist Peter van Missenbroek invented the Leyden jar, the world's first practical electrical capacitor, allowing experimenters to store high-voltage static charges in glass jars lined with metal foil. In 1774 AD, Swiss inventor Georges Louis Lesage constructed one of the earliest electrostatic telegraphs in Geneva. His system utilized 24 separate insulated wires strung between two rooms with one dedicated wire for each letter of the alphabet. At the receiving end, each wire connected to a lightweight pith ball. When a static charge surged down a specific wire, the corresponding pith ball repelled and jumped, indicating the transmitted letter. Lesage's electrostatic telegraph, along with similar multi-wire designs tested across Europe, proved completely impractical for real-world commercial use. Static electricity operated at immense voltages but minuscule currents. In humid air, the electrostatic charge leaked off the wires within a few meters, causing the signal to vanish entirely. Furthermore, stringing 24 separate insulated wires across miles of countryside was an economic and engineering impossibility. For electrical communication to become viable, science needed two fundamental breakthroughs: a continuous, reliable source of low-voltage electrical current, and a physical mechanism that could translate electrical current into visible or mechanical motion at a distance. The first breakthrough arrived in 1800 AD, when Italian physicist Alessandro Volta invented the voltaic pile. By stacking alternating disks of zinc and copper separated by cardboard soaked in saltwater brine, Volta created the world's first chemical battery, providing a steady, continuous flow of direct electrical current. The second breakthrough occurred in 1820 AD in Copenhagen, Denmark, when physicist Hans Christian Ørsted discovered that an electric current flowing through a wire created a magnetic field that deflected a nearby compass needle. For millennia, electricity and magnetism had been treated as two completely unrelated forces of nature. Ørsted had proven they were inextricably linked. Within months, French mathematician André-Marie Ampère quantified the magnetic force generated by electric currents and suggested that a telegraph could be built using a series of deflected magnetic needles. In 1825 AD, British electrical pioneer William Sturgeon advanced this principle by inventing the first practical electromagnet, wrapping bare copper wire around a varnished iron core. When current flowed, the iron became magnetized, lifting heavy iron weights, but dropped them the moment current stopped. However, Sturgeon's electromagnets could not operate across long distances because current dissipated rapidly over long lengths of wire. The critical scientific solution was uncovered between 1828 AD and 1831 AD by American physicist Joseph Henry in Albany, New York. Henry made a profound mathematical distinction between two types of electrical circuits: quantity circuits requiring high current in parallel, and intensity circuits requiring high voltage pushed through 1,000s of turns of fine copper wire insulated with silk thread. Henry proved that by matching a high-voltage series battery to an intensity electromagnet wound with 1,000s of feet of fine insulated wire, an electrical signal could travel through more than 1.6 kilometers of wire without losing its magnetic force, successfully deflecting an armature to strike a mechanical bell. Armed with these electromagnetic principles, European inventors raced to build commercial electric telegraphs in the 1830s AD. In 1832 AD, Russian diplomat Baron Pavel Schilling demonstrated an electromagnetic needle telegraph in St. Petersburg using 6 magnetic needles. In 1833 AD, German mathematicians Carl Friedrich Gauss and Wilhelm Weber strung 1 kilometer of double wire over the rooftops of Göttingen in Germany, connecting their physics laboratory to the astronomical observatory to deflect a heavy magnetic mirror. In Britain, William Fothergill Cooke and Charles Wheatstone patented their famous 5-needle telegraph in 1837 AD, installing it along 21 kilometers of the Great Western Railway between London Paddington Station and West Drayton. The Cook and Wheatstone 5-needle telegraph was an ingenious mechanical design. Its visual display consisted of a diamond-shaped board painted with 20 letters of the alphabet, beneath which hung 5 magnetic needles controlled by 5 separate copper wires running along the railroad tracks. When an operator pressed 2 keys on the sending console, electrical currents flowed down to specific wires, deflecting to needles simultaneously so that their points converged at the intersection of a single letter on the diamond grid. While intuitive, because railway workers could read letters without learning a code, the system had massive technical drawbacks. It required 5 or 6 expensive copper wires, omitted 6 letters of the English alphabet C, J, Q, U, X, and Z, and possessed 0 recording mechanism. If an operator looked away for 1 second, the message vanished forever. While European inventors built complicated multi-wire machines with swinging needles. An American portrait painter, with 0 formal scientific training, was about to revolutionize telecommunications through radical simplicity. Samuel Finley Breeze Morse, born in Massachusetts in 1791, A.D. Morse studied painting at Yale College and the Royal Academy of Arts in London, becoming a celebrated artist and co-founding the National Academy of Design in New York in 1826. Yet, despite his artistic success, Morse's life was reshaped by a devastating personal tragedy. In February 1825 AD, while Morse was in Washington, D.C., working on a $1,000 portrait commission of the Marquise de Lafayette, a courier on horseback delivered a letter from his father. His beloved 25-year-old wife, Lucretia, had fallen gravely ill following the birth of their 3rd child. Morse packed his paints and rushed northward by stagecoach and horse across frozen winter roads. But the journey took days. When Morse finally reached his home in New Haven, Connecticut, he was shattered to learn that Lucretia had died days earlier and had already been buried in the cemetery. The agonizing realization that his wife had suffered and died alone, and that physical distance had prevented him from receiving the news in time to say goodbye or attend her funeral, carved an unhealable wound into Morse's soul. He became consumed by the conviction that human thought should travel across continents at the instantaneous speed of lightning. In October 1832 AD, at the age of 41, Morse boarded the packet ship Sully in France to sail back to New York after studying European art during the transatlantic crossing. Morse conversed with passenger Dr. Charles Thomas Jackson, a physician and chemist who demonstrated an electromagnet and described European electrical experiments. When Jackson explained that electricity appeared to flow instantaneously through any length of wire, an epiphany struck Morse. He declared, "If the presence of electricity can be made visible in any part of the circuit, I see no reason why intelligence may not be transmitted instantaneously by sound or light." In his sketchbook, Morse laid down 3 core principles. Use only 1 single wire with an earth ground. Use a single electromagnet to mechanically mark moving paper tape, and encode language into discrete pulses separated by pauses. Returning to New York, Morse lived in severe poverty. Appointed as an unpaid art professor at New York University in 1835 AD, surviving on crackers and tea in a single studio room on Washington Square. In this room, Morse built his first crude working prototype using an old wooden canvas stretcher frame. A clockwork mechanism pulled a ribbon of paper across a wooden roller, while a heavy lead pendulum carrying a graphite pencil swung above the paper. When a pulse of current energized an electromagnet, the magnet pulled the pendulum sideways, drawing triangular zigzag peaks on the moving paper. Although Morse's 1835 AD prototype proved that an electrical pulse could mark paper, his original method of encoding language was deeply flawed and hopelessly slow. Morse did not initially believe letters could be transmitted directly. Instead, he devised an elaborate numerical dictionary system where every word in the English language was assigned an arbitrary multi-digit number, such as 14 for the 215 for war and 462 for peace. To send a message, the operator had to look up each word in a 1,000-page dictionary, assemble metallic-type slugs with notched teeth into a wooden rack called a portrue, crank the rack through a contact breaker, and at the receiving end, look up the recorded numbers in the dictionary. It was slow, prone to error, and incapable of transmitting proper names or unusual words. Furthermore, beyond 40 feet of wire, Morse's weak battery and crude coils failed to move the pendulum. In early 1837 AD, Dr. Leonard Gale, a professor of chemistry at NYU, inspected Morse's crude apparatus and diagnosed the electrical flaws. Morse was powering his circuit with a single voltaic cup, while his electromagnet had only a few loose turns of thick wire. Gale showed Morse how to replace his weak battery with a high-voltage, Cruikshank trough battery containing 20 pairs of plates in series, and how to replace the crude magnet with an intensity electromagnet wound with 100s of turns of fine insulated copper wire based on Joseph Henry's research. When Gale completed these modifications, the signal instantly surged through 10 miles, 16 kilometers of wire strung back and forth across the lecture hall, deflecting the pencil with crisp authority. On September 2, 1837 AD, Morse demonstrated his 10-mile circuit at NYU. In the audience was a 29-year-old recent NYU graduate named Alfred Vail. Vail's father, Stephen Vail, was the wealthy owner of the Speedwell Iron Works in Morristown, New Jersey. Alfred Vail was a gifted mechanical inventor and machinist who instantly recognized the telegraph's revolutionary potential. Vail offered to provide $2,000 in funding, machine shop facilities, and his mechanical skills in exchange for a 25% share in the telegraph patent. On September 23, 1837 AD, Morse, Gale, and Vail signed a formal partnership agreement. At Speedwell Iron Works, during the freezing winter of 1837 AD and 1838 AD, Alfred Vail and young apprentice William Baxter labored 14 hours a day. Vail discarded Morse's clumsy wooden picture frame and lead pendulums, replacing them with precision-machined brass gears, polished steel armatures, and finely balanced electromagnetic registers mounted on solid mahogany bases. But Vail's greatest contribution was not mechanical, it was conceptual. Recognizing that Morse's numerical dictionary was an absurd bottleneck, Alfred Vail insisted the system must transmit letters of the alphabet directly using short and long pulses, dots and dashes. To optimize transmission speed, Vail visited the printing office of the local Morristown newspaper, the Kemble's Press. In 19th century AD printing, compositors set text by hand from partitioned wooden trays, called typecases. Because type foundries manufactured lead letters in proportion to their natural occurrence in English literature, Vail counted the lead type in each compartment. In a standard font of 100,000 characters, Vail discovered that the compartment for E held 12,000 pieces, T held 9,000 pieces, A, O, I, N, and S held 8,000 pieces, while J and X held 400 pieces, and Q and Z held barely 200 to 400 pieces. More than 110 years before Claude Chappe formalized modern information theory, Alfred Vail created the first practical frequency-based data compression algorithm in history. Symbol length was made inversely proportional to letter frequency. Vail assigned the simplest, shortest signal 1 single dot to the most frequent letter, E. The second most common letter, T, received 1 single dash. Common letters received short codes, A was dot dash, I was dot dot, while rare letters received long codes, Q was dash 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 Z, was dash 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 Z, was dash 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 dot closing parenthesis. By optimizing the code to letter frequency, Vail reduced the total transmission time for an average English message by more than 50%. Vail established strict mathematical timing ratios based on a single fundamental unit of time known as the dot duration. 1 unit, in this temporal architecture, 1 dash equals exactly 3 units of time. The silence between dots and dashes within the same letter equals 1 unit. The silence between separate letters within a word equals 3 units. Finally, the silence between distinct words equals 7 units. This rigid mathematical structure ensured that whether an operator transmitted slowly at 10 words per minute or rapidly at 35 words per minute, the relative temporal geometry remained perfectly stable and The original 1838 AD, American Morse, code included variable length dashes and internal spaces within 6 letters such as C as dot space dot dot and O as dot space dot. While fast, these internal spaces caused errors on noisy lines. In 1851 AD, European telegraph engineers in Vienna and Berlin revised the system into continental Morse code, eliminating internal letter spaces and standardizing all dashes to 3 units. In 1865 AD, this standard was officially adopted in Paris by the International Telegraph Union as International Morse Code, establishing the universal standard recognized worldwide today. To overcome electrical resistance that caused signals to attenuate over long distances, $V equals I times R dollar. Morse, Gale, and Henry developed the electromagnetic relay. A relay acted as an electromechanical switch, an amplifier. A faint current arriving after 40 miles passed through 1,000 of turns of microscopic wire, pivoting a lightweight armature across a fraction of a millimeter to close to silver contacts. This closed a local secondary circuit powered by a fresh, high-powered battery, supplying strong current to operate heavy recording styluses or trigger the next relay. Through cascaded relays, electrical signals could regenerate indefinitely across 1,000 of kilometers with zero loss of strength. On January 6, 1838 AD, at Speedwell Ironworks, Alfred Vail tapped out the first alphabetic Morse code message across 2 miles of wire. A patient waiter is no loser, but years of political indifference and poverty followed. In 1838 AD, Morse demonstrated the system to Congress and President Martin Van Buren, but the economic panic of 1837 AD left the government with zero funds. In Europe, Britain and France rejected Morse to protect domestic monopolies. Returning to New York, Morse lived in extreme penury between 1839 AD and 1843 AD, pawning belongings and enduring ridicule from skeptical politicians who compared the telegraph to mesmerism and astrology. On March 3, 1843 AD, on the final night of the legislative session, Congress narrowly passed a bill granting $30,000 to construct an experimental 40-mile, 64-kilometer telegraph line between Washington, D.C. and Baltimore, Maryland. When Morse woke up the following morning, Annie Ellsworth, daughter of the patent commissioner, delivered the news. In gratitude, Morse promised Annie she would choose the first official message. Morse hired mechanic Ezra Cornell, later founder of Western Union and Cornell University, to lay the line. Cornell initially tried burying lead-sheathed cables underground, but water seeped in and destroyed the insulation. Cornell quickly pivoted, stringing iron wire overhead on 25-foot chestnut poles, insulated with glass doorknobs to prevent current leakage. On the morning of May 24, 1844 AD, officials gathered in the old Supreme Court chamber in the Capitol in Washington. Samuel Morse sat at his brass key, connected to the overhead wire running to Baltimore. In Baltimore, Alfred Vail waited beside his recording register. Annie Ellsworth handed Morse her chosen text from Numbers 23:23. "What hath God wrought?" Morse tapped the 29 characters in rhythmic pulses. 40 miles away, Vail's register scored the embossed dots and dashes onto paper ribbon. Vail read the tape and telegraphed the exact words back to Washington. The room erupted into applause. The electronic telecommunication age had officially begun. In the early years, all messages were recorded physically on paper tape. However, operators working 10 to 12 hours a day realized their ears recognized the distinct acoustic cadence of the machinery. The electromagnet's downward strike made a sharp click, and the spring return made a clack. Operators discovered they could transcribe messages in real time at over 30 words per minute, purely by listening to the rhythm, completely ignoring the paper tape. Although managers initially banned acoustic reading, empirical tests proved it was 3 times faster and produced far fewer errors than visual reading. Manufacturers eliminated heavy clockwork registers, introducing the telegraph sounder, a minimalist brass rocker arm mounted on an acoustic wooden-sounding box that amplified the clicks. Paired with the sounder was the iconic telegraph key, or straight key, a spring-loaded brass lever with platinum contacts and a hard rubber knob. The key became an extension of the operator's hand, allowing a skilled telegrapher to translate human language into electrical pulses with the rhythmic grace of a musician. The overland telegraph network expanded rapidly across North America and Europe. In 1856 AD, Hiram Sibley consolidated regional lines into Western Union. In October 1861 AD, Western Union completed the first transcontinental telegraph line to San Francisco, linking the Atlantic and Pacific coasts. The transcontinental line dealt an immediate fatal blow to the famous Pony Express, which shut down after just 19 months of operation. A dispatch that previously took 10 days on horseback was delivered in one fraction of 1 second. The telegraph transformed industry, journalism, and timekeeping. Railroads adopted telegraph dispatching in 1851 AD to coordinate single-track lines, eliminating catastrophic head-on collisions. In journalism, the high cost of telegraph tolls led 6 New York newspapers to form the Associated Press in 1846 AD and prompted Paul Julius Reuter to found Reuters in 1851 AD, giving birth to the inverted pyramid writing style, where critical facts led every story. Global financial markets synchronized stock and commodity prices in real time. To eliminate conflicting local solar times across railroad routes, observatories broadcast standard time pulses over telegraph wires, leading directly to the global establishment of standard time zones in 1883 AD. While overland wires conquered continents, oceans remained impenetrable barriers. Sending a message between London and New York required a 10-14-day steamship voyage. The breakthrough in underwater insulation arrived with Gutapasu latex from Malaysian trees. In 1850 AD, a cable crossed the English Channel. In 1854 AD, Cyrus Westfield formed the Atlantic Telegraph Company to lay a 3,200-kilometer cable across the North Atlantic seabed from Ireland to Newfoundland. After failed attempts in 1857 AD, a cable was completed in August 1858 AD, allowing Queen Victoria to exchange greetings with U.S. President James Buchanan, but Dr. Edward Whitehouse mistakenly pumped 2,000 volts into the line, burning through the insulation and killing the cable after 3 weeks. Physicist William Thomson, Lord Kelvin, solved the problem with his law of squares, proving undersea cables acted as colossal capacitors requiring low voltage and ultra-sensitive receivers. Thomson invented the mirror galvanometer and siphon recorder. In 1866 AD, Cyrus Field chartered the SS Great Eastern, the only ship large enough to hold 4,500 tons of armored cable. On July 27, 1866 AD, the Great Eastern landed the permanent transatlantic cable in Newfoundland, uniting Europe and America permanently. In warfare, Abraham Lincoln spent hundreds of hours in the War Department Telegraph Office directing Civil War armies in real time. While the Military Telegraph Corps strung 15,000 miles, 24,000 kilometers, of tactical field wire, in geopolitics, British cryptanalysts in Room 40 intercepted and decoded the encrypted Morse transmission of the Zimmermann telegram in January 1917 AD, exposing Germany's proposal of a military alliance with Mexico and propelling the United States into World War I. In 1887 AD, Heinrich Hertz proved electromagnetic radio waves existed. In 1894 AD, 20-year-old Guglielmo Marconi realized radio waves could transmit Morse code without wires. In 1895 AD, Marconi added grounded aerial antennas to expand range. And on December 12, 1901 AD, he achieved the first transatlantic wireless transmission, sending the Morse letter S3 dots from England to Newfoundland. Wireless Morse revolutionized maritime navigation. In 1906 AD and 1908 AD, international conventions established the Universal Distress Call, SOS dollar. Contrary to popular belief, SOS does not stand for Save Our Ships or Save Our Souls. It was chosen solely for its unmistakable acoustic rhythm 3 dots, 3 dashes, 3 dots sent without internal pauses, as one continuous presign, cutting through severe atmospheric static. The defining test occurred on April 14, 1912 AD, when the RMS Titanic struck an iceberg. Marconi operators Jack Phillips and Harold Bride transmitted CQD and SOS signals until power failed. 58 miles away, operator Harold Cottam aboard the RMS Carpathia heard the distress calls. The Carpathia raced through ice fields, rescuing 705 survivors from lifeboats. The disaster led the 1914 AD SOLAS Convention to mandate continuous 24-hour Morse radio watches across all ocean-going vessels. Morse code was the world's first practical binary digital telecommunication system, translating human language into discrete on-off states 1 south and 0 south. Alfred Vail's letter frequency optimization was the direct intellectual ancestor of modern Huffman coding and entropy compression that powers internet data today. The telegraph relay was the mechanical forerunner of the vacuum tube, the transistor, and the microchip logic gate, while Émile Baudou's 1870 AD 5-bit code evolved into ASCII and UTF-8. While commercial maritime Morse was retired in 1999 AD for satellite systems, Morse code remains vital. Over 700,000 amateur radio operators use continuous wave CW Morse, capable of punching through extreme noise on low battery power when natural disasters or cyber attacks knock out internet grids. In aviation, navigational beacons still broadcast Morse identifiers. In medicine, assistive switches, triggered by eye blinks or cheek twitches, allow paralyzed patients with locked-in syndrome to communicate via Morse code. The invention of Morse code began in 1825 AD with the grief of a young painter weeping over a letter that arrived too late to say farewell to his dying wife. Driven by that tragedy and forged through the collaborative genius of artists, machinists, and physicists, Morse code collapsed the vast geography of the Earth. By transforming thought into pulses of lightning, it created the planetary nervous system that defines the modern connected world.